Well, good morning, grade 12s. Welcome to, I think, our last week of this. So, yeah, getting there. And hey, we got something fun this week. Okay, quantum physics. This is the coolest stuff like ever. Okay, basically. So, yeah, let's get right into it. So, I just want to summarize what we've done so far. Basically, we're still talking about light. We haven't ended that conversation. That's why we didn't do a unit test. I might as well just finish these last few lessons on quantum, and that's it. Okay, and then this will be it for our unit on light. Really, it's I've got it broken down as two separate units, waves and light and quantum, but really it's the same thing. All right, so look, here's the story so far. Okay, and we go all the way back to Huygens and Newton with their two competing theories way back in the 1600s, okay, just to summarize what we've learned so far. And remember, Huygens proposed a wave model. Newton proposed a particle model, okay? For the next 200 years or so, or 150 years, I guess, in schools, they taught Newton's model. And the reason why was because Newton was considered one of the world's greatest geniuses because of his work on gravity. Not because his theory was better. That's unfortunate how that worked out for Huygens, but yeah. Anyway, in the mid-1800s, we discovered interference of light with Thomas Young's experiment and the double slits. That's a wave phenomenon. There's no way Newton can account for that in his theory. There's no way his theory could be modified to account for it. There has to be waves in order to have interference. And so that's a no-brainer there. And we've seen several examples of interference since, like thin film interference, single slit interference, okay, so there's double slit, single slit, thin film interference, air wedge interference. We've seen polarization, okay, which shows that the waves are crests and troughs and not longitudinal waves with compressions and rarefactions. We've seen other experiments that we didn't really get into, like scattering of light. For example, the sky is blue because light is a wave. Like I look out the window right here this morning, it's a beautiful blue sky. That's called Rayleigh scattering, and that's a wave phenomenon, and it's more evidence that light is a wave. Okay, and so this has been a well-established thing. And when they discovered electromagnetism, okay, in the mid-1800s, that finally put to rest the problem of light being able to pass through a vacuum. And so it seems like we've got everything in order. Light is a wave, and we've got the greatest theory ever put together. Okay. The electromagnetic wave model. Okay, so I summarized that for you here at the beginning of, I know that we just did this, but anyway, I put a little summary of that in here in these notes. I'm not going to read through all these notes. I already went through this lesson with you, the very last lesson that we did. So life is a self-propagating disturbance in an electric field. The electric fields are initially caused by accelerating charged particles. So how do you make an electromagnetic wave? We can do it artificially, okay? All we have to do is accelerate electrons kind of up and down an antenna. So like, let's say, for example, I have an antenna. I'll just zoom in on this little picture here. If there's an antenna right here, okay, and that's my antenna, that z-axis there is just like a wire, basically. And all I have to do is send the electrons up and down, kind of like alternating current. If I put alternating current in that wire, as the electrons move up and down, they will create a change in their electric field that surrounds them. It'll move its electric field, and then that will induce a magnetic field. And so here you can see, this is the electric field. The blue indicates the electric field disturbance. Okay, part of the wave. And this here is the magnetic field, which gets induced by changes in the electric field. And this thing propagates out at c, the speed of light. Okay, and so you can see its velocity. And they were actually, like I said, the most successfully tested theory in history. Okay, probably pretty close to this very day. Okay, in other words, like they have tested this theory in many ways. It's predicted things, like we built radios and cell phones and Wi-Fi and all this stuff, all based on this theory. It's really incredible how this theory had changed the world. Like I put a little bit of a list of that here. radios, generators, transformers, motors, right, and so on. Like all of these things, crucial pieces of technology today, okay, absolutely crucial. Yeah, it's funny, electric motors, you know, of course I keep talking about my Tesla, but today my Tesla's in the service center and they gave me a loaner Tesla, and the loaner Tesla has full autopilot, which it drove me home, okay? Like mine doesn't have that. It costs, like I can get it for my Tesla, that's like $14,000 upgrade, so it's software upgrade, so like forget it. But anyway, this car had it and it was kind of cool. It drove me home on the Queensway and it only makes me touch the steering wheel just to say that, like, you know, I'm still paying attention, you know. But anyway, it drove me home, took the exit, and once I got on the city streets, I had to drive it. But anyway. Okay, getting back to this. So here's our full electromagnetic spectrum. Okay, I've got it kind of backwards here, but anyway, you know, the longest wavelengths are radio waves, and here, the shortest wavelengths over here, gamma rays. Okay. So it looks like we've got everything lined up. We've got our wave theory of light. We have electromagnetic interactions. So this electromagnetic wave mechanical model looks like it was actually considered the greatest scientific achievement of all time. Okay, now in the mid 1800s, there, you know, maybe history did not have a lot of scientific achievements before then, but you got to remember, like, this was an amazing time for science. Like, they really established incredibly well the scientific method at this time that we still use today. Darwin came up with the theory of evolution, right? Pretty close to this time. Einstein was born just at the end of this, at the end of the 1800s, and then he comes with theory of relativity, right? Like this was an amazing time, guys, like really amazing. Okay. However, okay, the story gets crazy from here. So getting back to light, you know, it looks like everything's perfect. And the only thing that was missing, okay, and I'm just going to say this, the only thing that was missing was what was still necessary was how to answer this question. How do atoms emit and absorb light? So this was a question that had been left unanswered. Like, we can make a radio antenna that will emit radio waves, and that's a form of light. But we know that atoms emit light all the time. So for example, when I turn on a light bulb, those atoms start emitting light. But how do they do it? What physically are the atoms doing when they emit light? How come my table in front of me doesn't emit light? It only reflects light. At least it doesn't emit any light that I can see. Okay. And by the way, you know, like, it's not really emitting any light at all. Okay, maybe there's some infrared light because of the heat, but really there's basically atoms at room temperature are not really emitting light, okay, in most cases. And the thing is, why not? Okay, so that was one of those questions. And it turns out that answering this question, how do atoms emit and absorb light, it really turned their brains around. I mean, like, so they went down the rabbit hole. I think I was telling you this last week. So they went down the rabbit hole, and that's an expression from Alice in Wonderland. Like, scientists were confident that they would answer all questions, okay, in the next 20 years. Once they could answer this one, basically they would have it all figured out. So they needed a model for the atom, right? So atomic models. Now, you know something that they didn't know. Okay, you know already, based on what you've learned in science and chemistry and everything else, what atoms look like. They didn't know. Okay, and so what happens is that atomic model that you're seeing, and I hope you appreciate the atomic model that you've seen already, is a very strange thing. Like, it's very bizarre. What the electrons are doing in there, okay, the orbitals that they occupy and stuff like that, it's bizarre. And I want to always emphasize that to students because they don't appreciate that it's bizarre. Like, you know, for example, you know, 2 electrons go in the first orbit and only a maximum of 2. Why only 2, right? we have this thing called the Pauli exclusion principle. I'll explain that later, but you should have learned about it in chemistry class. There's only two, okay? And there's plenty of room. There should be room for 100 electrons in there, but only two. And it's always only two. Every orbital has up to 2 electrons, and no more than 2, okay, can go in there. The other thing is there's no energy level, there's no orbital spot between the first and second orbit, right? So the first orbit has a certain energy level, and then the second orbit has another energy level. There's nothing in between. You can't have anything in between those 2 orbits. So it's almost like saying if our solar system was like this, it's like, let's say Mercury was the first orbit, Venus was the second. Well, you couldn't have an orbiting rock in between those 2 things, right? But does that make any sense? And the answer is no, not in orbital mechanics. You could have rocks and stuff floating around anywhere. Okay, so the thing is something strange is going on, and I hope in this week here you'll appreciate that. Okay, so, all right. I just want to now get into the quantum theory. So what we're going to do in quantum theory, okay, just before I get ahead of myself, we're going to answer this question. How do atoms emit and absorb light? That was our next task, right? It was thought originally that, okay, the original idea was thought that the electrons, they had already theorized that it was the electrons that are emitting light. Since the protons were stuck in the nucleus, they had sort of come to that conclusion, right, with Bohr's experiment, okay, Rutherford and Bohr, the alpha particle experiment, and they knew that the electrons were the ones that were able to move, okay? And so the original idea was that here you have your nucleus, okay, and what the electrons were doing is actually orbiting. And so I'll just put them there, actually, whipping around, sort of like the planetary model. Okay, so whipping around your nucleus. And while they whip around, they would emit waves. Okay, so that would be light. A light wave coming off. Just like an antenna with the electrons going up and down. It's logical, right? But here's the thing. If the electrons are doing that, they would always be emitting radiation. So if Earth was an electron going around the sun, it would be emitting radiation constantly because it's always orbiting, right? And the thing is, radiation is energy. So if Earth was emitting radiation like that, its orbit would decay. It would slow down because you can't get energy from nowhere, right? And so as the electron emits this energy, it would slow down. And anything that slows down around the nucleus should fall in. Like if Earth were to slow down in its orbit, gravity would pull it towards the sun even closer. It would spiral down, eventually merging with the sun. Okay, but here's the thing. Electrons never do that. They absolutely never do that. Okay? And what about an atom that's not emitting any light at all? Okay, an atom that's not emitting any light at all, what are the electrons doing? Well, if they were orbiting around, they must release electromagnetic energy if they're orbiting, because all charged particles do that. Okay, if they spin in a circle, it's just that's their electric field will change. If the electric field changes, you're getting light that's being emitted from that. But here's the weird thing. Atoms that are not emitting any light, what are the electrons doing? Well, the only conclusion you can say, and this is what Niels Bohr came up with, the only conclusion you can draw from an atom that's not emitting any light, like a cold atom, let's say, is that the electrons aren't moving at all. Okay? If they're not moving at all, they should fall in. Because what's preventing them from falling in? They're attracted to the protons in the nucleus, right? But they don't fall in. So something is really strange that's going on there, and that's what now they have to figure out, right? Okay, so look, blackbody radiation. So blackbody radiation is the way atoms emit light. So I'm gonna try to explain to you what a blackbody is. So a blackbody is an object. Okay, did I define it here? I don't think I did. Okay, so a black body, okay, a BB, black body, is a perfect absorber and emitter of light. Now what that means is it can absorb all wavelengths, I'll just use lambda, and it also can, and therefore it would appear black. Because if you absorb all the colors of white light, what's your color? Well, it would be black. Okay, so you know, a red shirt absorbs all the colors except for red, right? A white shirt is reflecting all the colors, but a black object would absorb all the colors, okay? And it can emit all the colors when hot enough, okay? So you know, the classic example is a coal in a barbecue, let's say. When the barbecue is cold, what color is the coal? Well, it's black, okay? So it's an absorber of light in that case. But when you heat it, it starts to glow, okay? Now at first it'll glow red, but if you get it hot enough, white hot is hotter, okay, than red hot, okay? So like a white hot coal, like if you may be sitting around a fireplace and you see the white hot coals in there, the white hot coals are the hottest ones, okay? If the fire isn't cold enough or isn't hot enough, you might only get red coals, okay? So like it depends on temperature, but that's a black body. Okay, basically. Now, it's kind of a theoretical object, but we have several examples in nature. Basically, you can think of an atom as a black body, really. Atoms can absorb light. So the atoms in my table in front of me are absorbing light right now. I have a black pair of pants on. They're absorbing light. Okay, you know, and if we set them on fire, of course, these things will start emitting light. And that's it. Okay, so basically, we're just talking about matter itself and how matter absorbs and emits light. So, here's the problem. When you try to model, okay, radiation that comes from a black body. Now, by the way, we could use the sun. The sun is very hot, okay? And if it were to lose its nuclear power, that powers it in its core, like runs out of fuel, let's say, it's going to turn basically black. It won't become a black hole, it's not big enough, but it'll be a dark object, right, when it cools down. Okay, like we call it a black dwarf or whatever. And it will be just a ball of gas that's extremely cold, okay? And okay, so the deal is, oh my phone just started talking to me. But anyway, they were never able to explain how black bodies emit light, okay? So for example, take the sun. The sun is basically a black body that's hot enough that it's emitting all the visible wavelengths that you can see. Now, what it should be emitting is radio waves and so on, but when you try to use the wave model to predict, okay, so here's the deal, I'm going to underline this, I bolded it, but you could never get the wave model to accurately model radiation coming from the sun. It just doesn't work. Okay, it doesn't work. So, you know, you turn on a light bulb, what kind of radiation should come from the light bulb? Well, the wave model should be able to predict what kind of radiation will come from something like a light bulb at a whatever given temperature, right, of the light, or the filament in the light bulb. And the thing is, when you use the wave model to try to predict what radiation comes from the sun or a light bulb or the fire or whatever, it fails every single time to predict that. Okay. Now, there's a famous example developed by Rowley and Jeans. Okay. And Rowley and Jeans are the names of two scientists. I don't know their first names, but anyway, Rowley and Jeans. Rowley was the guy who figured out why the sky was blue, so we call it Rowley scattering. Let's just put it this way. They're both experts in the wave theory. Okay. Now, what they did was they developed a prediction, and that we later called the ultraviolet catastrophe. Okay. And what happened is the wave model, so this is the EM model, that is so successful in every other way, okay, but it fails spectacularly to explain or to predict radiation at any wavelength shorter than violet, okay? So let me show you what the deal is here, okay? So here's the deal. Let's say you have an object that's at, you know, here, 5,000 Kelvin. That's pretty hot, okay? That's like getting to be like the photosphere of the sun hot, like hot enough. Now we can get objects that hot here, okay, that are that hot, but on a tiny scale, that emit light, you know, let's say like sunlight, okay? So here at 5,000 degrees Kelvin, what the wave model predicts, so the wave model predicts the dotted line, okay? Basically, this exponentially increasing intensity of light, okay, and let me explain what this is at the bottom. See, this is wavelength down here. So like down here, 3,000 nanometers, these are in the microwave range, okay, and infrared. And then we're getting over here, we're still in IR over here. Then we get into visible light, and then here is UV, okay, that's ultraviolet. And what happens is, so in other words, this is going from short wavelengths to long wavelengths, okay? Now what happens is at the beginning, the two curves line up pretty well, but then they start to diverge, and this curve, which is the prediction from the wave model, gets way out of whack and just keeps going up and up and up, okay? Which, by the way, would mean that the sun would be emitting not just toxic levels of ultraviolet light, like way more than it does already, but levels of X-rays and gamma rays that would basically destroy all life on this planet, okay? And life could not exist in the universe at all if this is really how it worked. So this wave model failed, okay? It's a major fail. So in other words, you come up with a theory, the electromagnetic wave model, and then we try to use this theory to predict how light will come from the sun, what kind of light would come from the sun, and you get this ridiculous prediction that has to be false, because if it were true, we'd all be dead. And so the thing is that the wave theory, for reasons that are hard for me to explain mathematically, okay, but Rowley and Jeans did it for you here, they're using the theory correctly. It doesn't work. So when you try to use the wave theory to try to explain how radiation comes from the sun, let's say, or any hot object, a candle, or the sun, or a flashlight, or whatever, a light bulb, it fails. You always get the same curve. In other words, even a light bulb, you turn it on, you're all dead. Okay? You get an infinite amount of energy. And why is that? Well, remember what I was telling you that they modeled the atoms like this as little oscillators? Okay, so they call them electron oscillators, where the electrons are just orbiting the nucleus. Well, if you're orbiting around like that and your orbit never decays, you've got an infinite amount of energy coming out of that atom. Okay, it never stops. And you see, the thing is that it just doesn't work. It's just not happening. Okay, so anyway, the other line here, the blue, I'll shade it in blue. This is the actual radiation that comes from an object at 5,000 degrees, okay, Kelvin, or at 5,000 Kelvin. So this is the actual data. So this is measured data, okay? And thank heavens it works like this, okay? So in other words, if you have an object at 5,000 degrees Kelvin, yes, it emits infrared light. Okay, so here's your infrared section here. That's all IR. Okay, lots of infrared light, some visible light. Okay, so it's gonna be white in appearance. We don't see the infrared, so it's gonna appear white with a slight maybe tendency towards the red and orange side of the spectrum. So like it'd be a yellowish, like our sun. Okay, but it drops off to zero very sharply. Okay, drops to zero at ultraviolet wavelengths or higher, or shorter, I should say. So the sun does emit a trace amount of ultraviolet light. That's what gives me a sunburn and gives those of you gifted with darker skin a suntan. Okay, that's ultraviolet light that does that, but it's only a trace coming from the sun. If it was a ton of ultraviolet light coming from the sun, doesn't matter how brown your skin is, you're going to be basically like your skin will be destroyed by that. Okay, ultraviolet light is ionizing radiation. It will break bonds in your skin. Okay, and your skin can absorb some of it with the pigmentation that you have, but like it's a good thing the wave theory isn't true, because you would get massive amounts of ultraviolet light. But then the X-rays, forget it, even more. Okay, and gamma rays are extremely deadly. Okay, so basically the sun emits 0 gamma rays, 0 X-rays, and just a trace of ultraviolet light. And even if we crank the temperature on the sun, like let's say you had a hotter sun somewhere like a blue hypergiant, well, that lean towards the blue end of the spectrum, even those don't emit any X-rays or any cosmic rays, or sorry, gamma rays, and even a trace of ultraviolet light. They're all the same. Okay, so if you had a hotter object, okay, it would look something like this. That would be a hotter object. Sort of emits more of everything, but it still drops off sharply right there at ultraviolet. Now they considered this a catastrophe for the EM theory. Why is it a catastrophe? Because the EM theory fails. It's a catastrophe. That's why it's a catastrophe. You got the greatest theory ever, guys. The greatest theory ever put together. The most successfully tested theory in the history of science. Okay? But it fails to explain this. And the attempts were made to modify the theory so that you would get the data here that actually comes from the object. And it fails. They fail every time. You couldn't modify the data. Trust me, they tried. Okay, they tried for decades to fix it. Doesn't work. Okay, so, this is why it was considered a catastrophe. You've got the greatest theory ever. What do we do now with the wave theory? Like, how do, of course we still have interference. So light is still a wave, but the wave theory itself seems to fail when you try to explain something basic like how atoms emit light. Okay. Anyway, so it was into this problem that Max Planck comes along. Okay. And Max Planck is more of a mathematician than a scientist. Okay. But he's working primarily in the field of thermodynamics. Okay. And what he did, which is like the study of heat. Okay. And he modeled the data mathematically. So in other words, he just took the actual data, like so the blue lines, okay, on that graph, and he said, look, he said you could get the experimental data, but you have to do one thing. You have to not assume, but like you have to use an idea, okay, that seems to be a radical departure from the wave idea, that instead of the light coming from the atom as a continuous wave, it seems to be emitted as a tiny bundle. And the tiny bundle he called quanta, and that's where the word quantum physics came from. Okay. Now the energy per bundle was a function of the color of light, which varies with wavelength, as you know. Okay. Now, these aren't waves really that he's talking about. He's just saying like a little bundle, it's like a little lump of something. So it's coming like a little lump. Okay, it sounds awfully like a particle. Okay, but the energy in the bundle depends on its quote color, and we use wavelength as a marker for color, right? And so he said the energy per bundle is given by this equation. Okay, and that's Planck's equation. And what happens is you can use this equation hc over lambda, or hf, as the energy per bundle. So let's say you were a bundle of red light. Okay. And did I give an example here? No, I didn't. Here, let me give you a little example here. So I'll just zoom in and I'll go IE. Let's say your wavelength is 600 nanometers. And that's for red. Okay? Then, therefore, the energy per little bundle of red light would be E equals hc over lambda. And his constant is this really tiny number, which makes sense when you think about it, because a little bundle of red light would be a very small little bit of red light. So 6.63 times 10 to the negative 34 times the speed of light, 3 times 10 to the 8. You'll need to use calculators for all these questions, times 600 times 10 to the negative 9. Okay, so you have to convert everything to standard units. So I'll do that right now. 6.63 exponent 34 negative times 3 exponent 8 divided by 600 exponent 9 negative equals, I get 3.32, sorry, times 10 to the negative 19. So this turns out to be 3.32 times 10 to the negative 19 joules. Now, I'm going to convert that to electron volts, which is something that we talked about in the electrostatics unit. You just divide by the charge on the electron. It has nothing to do with electrons. It's just an electron volt is 1 electron times 1 volt, but it's just another unit of measuring energy. Okay, I get 2.07 eV. Okay, so there's 1.602 times 10 to the negative 19 joules in 1 electron volt. So you just convert it. It's like your factor label method, right? Now, if I try that again for blue, okay, if I want to try it for blue, so let's span the visible spectrum. If I try blue light at 300 nanometers, okay, the energy, and I'll just give you the answer. Okay, I'll do it quickly. So it's going to be twice as much because it's half the wavelength anyway. I get 4.14. Yeah, it's exactly double. Okay, so here's the deal. Red bundles, red quanta, have less energy than blue quanta. In fact, blue quanta have twice as much. Now, if you go to ultraviolet, they have even more quanta, or sorry, more energy per quanta. Now, what is a quanta? Well, Planck doesn't really know. He just says, like, look, you're trying to model light like a continuous wave coming from the atom. It's not working. Okay? They seem to be emitting these little blips of energy. So when an atom gets hot, it doesn't emit a wave as if the electrons are just whipping around that nucleus, right? Just getting spun up by the heat or anything like that. It doesn't seem to do that. What seems to happen is it just emits a little, boom, little shot of energy, okay, that he called a quanta. And the energy per quanta varied with color according to his equation. Now, if you model the light like that, now you can get the predicted result. You get this graph that agrees with the measured data, okay? Now, he doesn't have a theory here. He's not really proposing a theory. He's just saying that that's how you have to model the radiation in order to get the correct result, okay? Now, what happens is, once you get to the ultraviolet range around 10 to 124 nanometers, it seems like the atoms are just physically unable to emit light shorter in wavelength than around 10 nanometers. Okay, it just can't do it. So the atoms, for whatever reason, has got some kind of physical limitation. They can only emit these little bundles up to a certain wavelength. After that, see what happens after that is the atom gets ionized. If it gets too hot, it gets ionized. Okay, so the electron just leaves the valence electron or whatever will just leave the picture here, escape the atom, okay? And then now it becomes an ionized gas, and that's kind of like a plasma. Now all the rules change, right? So the radiation coming from the atom will drop sharply to zero if you get too hot. Okay, now not to say that so the atom will continue to emit all the other wavelengths, but it cannot emit any wavelengths past that certain wavelength. In other words, there's a cutoff. You can only go this far, and thank goodness, because once you get to ionizing radiation, like ultraviolet and beyond, it becomes extremely toxic. Okay, and so anyway, nature got it just right. Okay, like it all shuts off at the ultraviolet range, so around 90 nanometers. That turns out to be a physical limit, 90 nanometers. But what's so special about that number, 90 nanometers? Why 90? Why doesn't it cut off at 100 nanometers? Well, for whatever reason, 90 seems to be the magic number. You cannot get, for example, any light at 89 nanometers or 88 or 87 or even 89.9, 90 nanometers, that's the cutoff. So it's like a threshold. Okay. Anyway, you try to understand this with a wave model, you can't understand it, right? So I can't sort of stress this enough. This is a total contradiction to the basic premise of the wave theory, okay? That light is a continuous wave. Like Planck is not talking about waves. I know there's the wavelength in here, but remember, wavelength is just a number, okay, that corresponds to a color, okay? Like, so when I say 300 nanometers, that means red, or sorry, that means blue. 600 means red, 500 or so means green, okay? But, so normally wavelength would be the distance between waves, and that's what gives the light its color. But what Planck is saying is that there's really no wave here, okay? So he's starting to sound like, things are starting to sound like maybe Newton was not so wrong after all. Maybe his basic idea that light seems to be coming out like a little particle, he called them corpuscles. Planck calls them quanta, okay? But maybe they're onto something there, because if you have this little pulse, well, what's the weight? Where is the two crests that are necessary to have a wave, okay? And so, anyway, and a wavelength for that matter. So this is in stark contradiction to the basic premise that light is a wave. Like if you take a theory apart at its foundation, we start with light being a wave, and now that seems to be falling apart, we're in big trouble with the wave theory, okay? And so, anyway, I'm going to leave it there for now. It's long enough for today. Tomorrow is a very important lesson on the photoelectric effect. This is really our last sort of big lesson here, Einstein and the photoelectric effect. The other lessons afterwards are pretty short, but tomorrow is a big one, and it's one of Einstein's. Einstein did not win a Nobel Prize for the theory of relativity, which he's most famous for. It's greatest work. He won it for this photoelectric effect, which you probably didn't know. Okay, so let's just show you the outline. And I'm going to make a few changes to this. All right, so here's what we did today. We're done this. Okay, so if you could please do that. And then tomorrow we're going to do the photoelectric effect. So that'll be tomorrow. Then we'll take care of some of these other things in one lesson. So we should be finished before the end of the week, no problem. We're not, I think I've told you this before, we are not doing the relativity quiz, so let's put a strike through that, because we didn't do the independent unit. Unfortunately for you, because that's a great unit. We're not doing radiation and radioactive decay. That was also in the independent unit, which we are not doing. So you can get rid of those things, okay, and all this junk at the end, okay? So when you look at this, there's not much left. We're going to do Compton effect and de Broglie wavelength. We're going to do these two together, so that's just one thing. And really, this one here is just a note that I have for you, okay? And you can just read it. It's very simple. So we're going to do all this week, no problem, and then that'll be it, guys. Okay, so anyway, do the first 6 questions. Super easy, just using Planck's equation. All the math, good news, really easy, okay, in this unit. So just go ahead and use it, and we'll get into the photoelectric effect next. If you have any questions about the wave theory or anything else, look, I know it's the end of the year, but I mean, just hang on a few more days, and then we'll be done, okay? So we will talk to you soon.